Hi everyone, this video is designed to help you out with assignments 6 and 7, I believe, in your resource pack, and we're going to be looking at different ways to calculate concentration. So we'll be looking at table T and the three equations that are directly or semi-directly associated with concentration, or how much stuff is dissolved in a particular amount of usually water, but really any solution. So we'll be focusing in on these three equations: percent composition by mass. So let's say what percent of whatever you're drinking at lunch is sugar. Parts per million, which is very similar. How, if you had a million molecules, how many of those molecules would be sugar or lead or any other dissolved substance? And also molarity, which is kind of the chemist's favorite, where we look at how much stuff expressed in this standardized unit of moles are dissolved in a particular amount or volume of solution. So what I've got for you is a sample problem where I've given you a mass of table salt, NaCl, that's dissolved in 100 grams of water, and I create a solution with a volume of 105 milliliters. And I want to know its concentration. And there are three different ways that I could calculate concentration depending on what unit I'm interested in. So if I had finished this sentence by saying find its concentration in percent by mass of NaCl, you would want to use the percent by mass equation, which tells us the mass of the part divided by the mass of the whole times 100. That times 100 is important because it's really going to differentiate the equation from parts per million calculation. So the mass of the part is the thing that I've dissolved, the thing that I'm interested in. And in this case, the thing I'm interested in is NaCl. And I need to know its mass. Well, good thing it told me 10 grams of NaCl is going to be my mass of part. The mass of the whole means the whole solution. So the NaCl and the water together. So in this case, I've got 10 grams of NaCl and 100 grams of water. And we're going to still be multiplying this by 100. That's, of course, going to give us a calculation of 10 divided by 110 times 100. Here, don't feel ashamed to let your calculator do the work. 10 divided by 110 times 100 will get you to your answer of 9.09%. So this particular solution is about 9% salt. That makes sense. 10 out of 110 gives you about 9%. Not so bad. And even though this next unit may not be as familiar as a percentage, it's actually exactly the same calculation. Even though percents are out of 100, parts per million are out of a million. So we're going to use the same numbers as before, just multiplied by a different factor. You'll see on table T that parts per million is represented as mass of solute divided by mass of solution times 1 million. Don't let this fool you. It's exactly the same equation as percent by mass. The solute is the part, the stuff that you've dissolved. The solution is the whole thing. It's exactly the same. The only thing that differentiates these two calculations is whether you multiply by 100 to create a percent, or whether you multiply by a million to get to parts per million. So I'm going to use exactly the same numbers. In this case, my ppm is going to equal mass of solute, 10 grams of NaCl, divided by the mass of solution, which again is going to come from 10 plus 100. I'll jump right to the 110 grams of solution as a whole, my salt plus my water. And now I just need to multiply times 1 million. I should get an answer that includes these numbers because I'm just adding a bunch of zeros on at the end. And again, don't be afraid to let your calculator do the work to double check yourself. 10 divided by 110 equals, then times a million, that's 6 zeros. You're going to get 90909.1. So let's just round that to 90909 parts per million. This is probably a little bit too precise, but that's okay. What this tells me is out of 1,000,000 particles, just over 90,000 of them are salt. So that seems like a lot, but this is a fairly concentrated solution to use parts per million for. Oftentimes, when you use this particular type of equation, you're going to get some very, very, very tiny number for mass of solute, oftentimes expressed in scientific notation. So maybe 2.0 times 10 to the minus fourth grams of lead. And that makes sense. You're not going to find lead dissolved in water in high concentrations, I hope. So oftentimes those parts per million calculations will be used for very small numbers, but in this case, it's perfectly acceptable to do this type of calculation. The only other thing I could ask you to do is find the concentration of that solution as expressed in units of molarity. And looking on your table T, molarity with its capital M is equal to moles of solute divided by liters of solution. Now this is different because we can't just plug in numbers for mass here. We've got to have moles and we've got to have liters. The problem told us that we had 105 milliliters, so we're at least close in getting a number here. But we only know that it's 10 grams of NaCl, so we've got two different conversions to do. First, I need to convert my 10 grams of NaCl into moles of NaCl. And don't fret if you have to do that, because right above the molarity calculation on table T, up at the top, there's this conversion that says number of moles equals the given mass divided by the gram formula mass. 10 grams just becomes our given mass. So in order to find moles, all I need to do is divide it by the gram formula mass of NaCl. If you go to your periodic table, you're going to find that the mass of NaCl is 23 grams per mole, and the mass of Cl is 35 grams per mole. So down here, we'll have 23 plus 35 grams per mole. And now you can just let your calculator do the work to convert that number into moles. So 10 divided by 23 plus 35. Be careful with parentheses if you're doing this on your own calculator. That gives me 0.172 moles. So now we have this component of our molarity equation. All we need are liters of solution. And like I said, the problem told us that we have 105 milliliters, which is close, but we need it to be in liters in order for this calculation to turn out correctly. So what I need to do is convert 105 milliliters into liters. In order to get rid of that M, folks, you have to know that 1 liter is 1,000 milliliters. And if you don't remember that, you can check out, I think it's table C on the front of your reference table, which is going to show you that milli is associated with 10 to the minus third. So what that means is we can take where our decimal point usually is and move it over 1, 2, 3 spaces to the left to make it smaller, and we'll end up with 0.105 liters. We now have our two pieces of our molarity puzzle, so we can just plug and chug. Our final molarity, capital M, is going to be 0.172 moles. Moles will never be expressed with a capital M. Always, always remember, molarity is the capital M, not the moles. We'll divide that by our 0.105 liters, and again, let the calculator do the work. 0.172 divided by 0.105, 1.64 molar. And that's it. This, I know, it looks like a bit of a pain, but the calculations aren't too bad. You can use your reference table T to help you along the way, but we've now found 3 different ways to express concentration. So I hope this helps you with assignments in your resource pack and problems on your practice test.